The next step in our story is very interesting. It's Alan Turing's invention of something called a Turing machine, which later in the history, by the 1960s, people can say that the Turing machine is something like a definition of the computer, or the Turing machine is maybe the best specification of what a computer fundamentally is. But at the time that Turing wrote the paper, he wasn't trying to make a contribution to the history of, say, mechanical computers or technology. He wasn't trying to invent a new technology. He was trying to solve a problem in the foundations of mathematics. And the problem had been posed in 1928 by David Hilbert, who was an extraordinarily influential mathematician, who posed a number of problems. This in 1928 was relatively late in his career, actually, and he posed similar problems as early, very early in the 20th century, in the 1900s. But this way that he posed the problem in 28 was, can anyone show that math is complete, that is like arithmetic and perhaps the calculus and so on, that those systems, given a certain set of axioms that define those systems, that we can derive all true statements that can be expressed in those systems. So can we show that anything that is true in math can be proven in math? And likewise, the question of whether math is consistent. Can we show that it's impossible to derive two contradictory results from the same set of axioms that define arithmetic or the calculus, etc.? Can we show that math is decidable? That is, is it possible to have a rule or an algorithm that can tell us in advance whether a given question has an answer in math? And so these were three challenges that Hilbert introduced in his 1928 address that are very famous in the history of mathematics, because shortly thereafter, a mathematician named Kurt Gödel, G-O-umlaut-D-E-L, showed, again in a very famous paper, that math could not be complete and consistent. So that if math was complete, it wouldn't be consistent. Any axiom set that is complete is inconsistent, or allows you to generate inconsistencies, and any axiom set that is consistent allows you to identify true statements that can't be proven within the system. So he basically showed that the answer to Hilbert's first two questions is no, and Hilbert and many others were very surprised by this and troubled by it, because the assumption had been that it must be true, we just have to show that it's true. So to have a mathematician show that it's false was a big wrench in the gears, so to speak, of the program. But Gödel's paper did not answer the decidability question, and it wasn't until 1936 that Turing, as well as another mathematician named Alonzo Church, published papers that showed that surprise, surprise, mathematics is not decidable either. That is, there is no rule that can tell us in advance whether a mathematical question has an answer. Now, to answer this question, Turing adopts an extraordinary strategy. He tries to define decidability or narrow down, hone in on what would make a problem decidable by imagining and trying to specify definitionally what is the process by which one decides an answer to a mathematical question. That is, how do we define the process by which a definite answer to a mathematical question is arrived at? For instance, how do we describe the process of finding the output value of a function given an input value? What is that action of answering a mathematical question. And his specification of what that is it's computation. Okay, so for a mathematical question to be decidable, or to have a definite answer, is for it to be possible to carry out a process, a rule-based process that arrives at a definite result on the basis of the set of rules that are followed. And so that is what Turing calls computation. Okay, and he tries to get even a little bit more specific in defining what computation is. The word computation and computer existed at this time, but they referred to basically a job that human beings could have. So if there were jobs for computers, and computers, the job posting would be computer needed, and it would be human beings applying for the job, because the human beings were the computers, right? Just like humans are doctors and carpenters and so on. Okay, and so what that job involved was doing things like writing out tables of the kind that Babbage's difference engine was supposed to write out. Okay, and so they would be given a task that required computation. Usually didn't involve a lot of creativity. It more was a kind of rote task that was repetitive, and they would have to, carry out a regular sequence of actions to get something like a list of numbers, where the output was written, across from the input for each row of a table, something like that. And so the question is, what is this action of computing? What is it for anything to compute, for a human being to compute, is really sort of the guiding question. What is it for something to compute, or what is a computation? And so he says, really, we need these elements. We need to recognize that the computer has a certain state of mind, that they are in some kind of cognitive state when they're engaging with whatever symbols they're engaging with in the process of trying to solve a problem. The symbols that they observe, are another part of the system. That's an essential element. And then they can take an action based on the combination of their state of mind and the symbols that they observe, And to try to keep things as simple as possible and really as essential as possible, the sort of bare bones description of what it is to compute. Turing says, imagine that all they can do is look at a single symbol at a time, and they can change that symbol, and they can change their mind, or they can change what symbol they're looking at. So really, they can only do one of three things. They might do a combination of them as a response to their state of mind and the symbol that they're observing. But they can only do one of these three things if we're going to define computation as strictly as possible. And to be even more definite, Turing describes these processes as being carried out by a machine. So he says, imagine a machine that can only read one symbol at a time, and then it based on the symbol it reads and the state that it's in, what he calls its M configuration, that's its state, that based on the symbol it reads and its current state, it takes an action, and the action is going to be some combination of three possible things. It's either going to change the symbol on the tape, it's going to move to the left or to the right, or it's going to change its own state. So there are three things that it can do, some combination of those three things, and it can't do anything else. But strangely enough, describing a machine that only does those three things and only responds based on that information, its current M configuration, its current state of mind, and the individual symbol that it sees. And with the assumption even that the symbols that it sees are on what Turing described as a tape that's run that is fed into the machine, or the machine starts with the tape in its mouth, so to speak, okay, with the tape under its eye at one particular place. And then it responds based on its mental state and the symbol that it looks at. And we even assume that this tape has a very small number of symbols, say just 1, 0, and X, or even just 1 and 0. We're able, with a tape that even just has 2 symbols, like say 1 and 0, we are able, in principle, to describe a machine that can compute any computable function. In other words, and that's an extraordinary result, but in other words, this machine that Turing described is a universal computer. This machine is able to carry out anything that would count intuitively as a computation. And the way that Turing shows that is by basically describing a system for producing instructions to a machine as to what rules it should follow in continuing to operate. So it's possible to program a Turing machine to imitate or to carry out operations in accordance with the programming of any other Turing machine. And this is what people mean when they describe such a machine as a universal Turing machine, distinguishing the universal Turing machine from a machine that's set up just to solve one or another, or just to carry out one or another particular program. The universal Turing machine is Turing machines considered under the light of the fact that they can be programmed to do anything that any other Turing machine does. So they can be programmed, again, to compute anything that is computable. Now, the other result that Turing draws from this is that some numbers are not computable. And the way that he arrives at that result is by describing or defining certain numbers that he can also show a Turing machine won't be able to produce as an output. And so some parts of math, the conclusion is, some parts of math we can't illuminate through computation. We can't find the right answer, or whether or not there is a right answer, through computation. Again, an extraordinary result, but not one that's so important for our class as the definition of computability and the scope of capacity of a universal Turing machine.